So Melissa, can you tell us a little bit about the topic that you are going to be teaching?
Okay, so this unit is a physics unit, and the specific piece that's part of this opening lesson is about trying to get students to talk to me about their ideas about sliding. So I'm trying to get at ideas about friction and maybe some ideas about weight, just to understand some of their initial ideas about forces.
So for the unit that you plan on teaching, some of the big ideas that you want to address are around forces.
Forces, this is sort of getting at some classical kind of Newtonian physics ideas of just getting kids to express their ideas about how forces interact to help explain how things are moving in everyday kind of motion, and then also that it would be like getting kids to see these everyday kinds of motions and be able to describe them and explain them using the conventions of physics. So like being able to, every kid might be able to tell you some story about something, a car moving down the road at 20 miles per hour, but I want them to be able to then see it the way that a physicist would see it, and be able to talk about speeds and accelerations and forces the way that physicists would describe and explain that same motion.
So are there some ideas that you're going to teach first? It sounds like you're going to get into a dynamics unit, or what's going to lead up to that?
So first I'm going to do a brief sort of mini unit, I guess, that gets at kinematics ideas, being able to describe motion without going into the explanatory ideas of forces. So being able to describe how an object is changing from one position to another over time, and then being able to talk about that in terms of speed, and then being able to talk about that in terms of velocity. And I'm going to have kids work on like looking at the phenomenon of something moving at a certain speed, measuring that phenomenon, and then graphing the data, so that they are also becoming fluent at those three sort of representations of the same description, so that they can tell me, like that car was rolling, that little cart was rolling down the hallway at this speed, but then they could also look at the graph and say, I can tell from the graph that the cart was moving at this speed. And that sort of lays the groundwork for being able to talk about acceleration when I get to Newton's laws, kind of explanatory ideas that I kind of need them to have that speed and velocity understanding and the graphical representations before they can
So it sounds
do a
like
lot of the acceleration ideas that are part of forces.
sounds like a few key prerequisite ideas that they have to get familiar with before they can move into dynamics, but also it sounds like you're trying to develop in them some competence with representations and how to use them.
Right. Like, I don't know that the ideas, ideas of speed and position and time, those are not new ideas. Kids have robust ideas about those descriptive parts of motion. They just maybe aren't using these conventions of physics of graphing and data to represent that motion. They're maybe using everyday things like miles per hour, and they're saying faster and slower, and they don't have sort of deep meaning attached to those words, and so it's more that I'm trying to flesh out a physics way of describing motion, so that then when we try to explain motion using forces, we're all sort of using the same language and these same representation conventions.
So there have been a lot of curricula out there that will address force and motion in different ways, and could you talk a little bit about how a typical curriculum might address this, and whether you see the typical approach as being something that's satisfactory, or how does it differ from how does it differ from what we consider big ideas in science that you want to address?
So I think probably the difference between what I'm doing and what I maybe could have done if I had just followed the curriculum that's given to me is, so, really, really standard traditional physics, it's almost feels like a math class in a way where you're just given an algorithmic way of solving problems. You're just given equations and quantities, and you're solving problems that
very
way.
math-based.
Right, and so you're given maybe an equation, and then maybe you do a lab where you demonstrate that the equation holds true or something like that. Then there's also curricula that flip that around where it's more of maybe the students are developing the conceptual understanding first, and then they're given the equation. But it's still about like confirming that the law holds true.
Yeah.
It's still kind of a confirmation style, and there's not as much emphasis on connecting ideas together, and certainly not really thought of as being like competing models for explaining a phenomenon. It's still sort of, there's one right way to explain this concept. So I think what I'm doing that's maybe a little different is I definitely follow more like the conceptual kind of approach where I work on, I want kids to build a concept first before we start doing an equation. But it's that I don't think the concept has to be totally detached from mathematical representations. So it's that I'm using all of those as models for, initially it's descriptive models, just different models for being able to see a phenomenon and describe it, and then later it's explanatory models, and I want those to be constructed from students' ideas and background knowledge that they're getting from some text that I'm giving them, and background knowledge maybe that they're gathering from their own data in class.
So you seem to be pulling together in the development of the models that you want kids to understand. You're going to, it doesn't sound like you're going to stand up in front of the room and just give an exposition of these. It sounds like you're going to draw in different experiences and try to get the kids to make sense out of the different experiences.
Right.
So you mentioned direct experience that they would have?
Right, so connecting, rolling something down a ramp or sliding something along their desk, connecting a measurement that they physically took or an observation that they physically experienced. But then maybe they're also reading, a little section from the text about Newton has these laws, and these are the relationships that Newton established, and then comparing maybe their own description to the law that Newton has, and hopefully they'll see connections, but maybe, it might be that they would begin to see that Newton's laws are like an idealized version of motion, and so they might also see things like no friction, a friction-free place, where is that? That they might start to see that in the real world, things don't always move in these ways that are idealized. There is no such thing as on Earth as an object that just keeps on moving forever.
So if I can go back to an idea that we were talking about just a minute ago and finish that, you were talking about drawing together different kinds of experiences. One is like firsthand experience I have with the rolling things, sliding things, then information out of texts, right? Are there anything else that you're going to have them try to triangulate with other experiences?
I guess maybe it's also that they're comparing across groups a lot of times too, so that they're getting not just their own firsthand experience, but that they're getting experiences from their classmates.
Are you going to do any kind of direct instruction with them that present an idea to them that they might not otherwise, or it may be impossible for them to discover this?
Yeah, I think I couple my own sort of me giving the direct instruction with a text providing information, or sometimes it might not be a text in the sense of words, like it might be a diagram or some data from something else, so that they are definitely being presented with something, with an idea. There's times like way down the road when we start representing forces with like force diagrams, where some kids will intuitively arrive at something like a force diagram, but I do just directly teach them the convention of representing forces with these arrows, and these arrows stand in for some force that you've now felt and measured. But
Why do you choose to do that through direct instruction? That piece, you seem to have a reason to do that piece.
I think because it's a convention that the world of physics has chosen to communicate this unobservable idea of forces in one way. And so, we represent it as an arrow, and the arrow begins and ends here, and it comes out of your object this way, and I think engineers do it a different way than physicists do, so it's even within like the physical science community, there's differences. So in order to be able to put up a representation on my projector and have it mean anything to kids, we have to sort of have come to a common agreement about how to represent things. And like I said, a lot of kids will get there intuitively, like they'll start to represent, instead of drawing a string that they're pulling, they'll just draw an arrow, but sometimes they'll draw it pushing instead of pulling.
Yeah.
That they'll do things as a push instead of a pull. And so we just have to change the way, come to an agreement about how to represent a convention.
So you mentioned a couple times the idea of explanatory models or some underlying explanation. And what are the explanatory, is there an explanatory model that you really want the kids to become really familiar with? And why would you think in terms of models as what you're basing your unit on?
So, so the phenomenon itself is motion.
By phenomena, you mean something that's
that
observable?
they can see, yeah. So the event in the world that kids are seeing is stuff moving. So it might be something rolling down a ramp or dropping from the balcony to the floor. So they see something moving, and then you can describe how fast it's going and how far it's going, and all of that's still a description. But when you want to say, well, why do I have to keep pedaling my bicycle to keep it going?
Yeah.
If I let off the pedals, eventually I glide to a stop. Like, why is that? If you start to ask the why question, then you need a theory of forces to be able to account for why is it that I would have to keep pedaling to keep my bike moving. And if I let off my pedals, my bike doesn't keep moving forever. It's eventually going to glide to a stop. So it's that I'm trying to have them generate and combine with Newtonian physics a theory of forces to account for the way that movement is happening on Earth. But you do hit some roadblocks, like in physics, when you get to an idea like inertia. There's no explanation for that.
Yeah.
It's just
hard to drill down
like,
farther.
Yeah,
than
it's
that.
just kind of you just stop at that idea. And so even though the question is kind of interesting, well, why would it do that? There is currently no explanation for that, and it's not even something that a physicist would seek to explain. So there's some places where I can't really keep pushing because there is no.
You just can't go any more fundamental than that.
Hit the ground. But really, it's that I'm trying to get them to sort out a force theory of accounting for the way that things move.
So
and then eventually, I don't think that this will be part of what you guys observe, but eventually I'm also connecting that to some ideas about energy. So that's the other sort of underlying, they did a theory of how mechanical potential and kinetic energy work together to account for movement that they're seeing.
So you've used a lot of language like why explanations, underlying, and accounting for things. So it sounds like the idea of a model being something that helps explain observations is important.
Yes.
And so does that mean that must mean something specific if you teach these explanations as models, as opposed to just, you could just go up there and give the kids the explanation. But how do you
Sure.
teach something like an explanation as a model? What does that mean in this case?
So I think in this case, it's that there's a big system of ideas and unobservable things, theoretical things that are like the current sort of best way to explain what's causing the phenomenon that you're seeing happening. And I guess when I think of it as models, it's that, you know, I could just teach them Newton's laws. Those are all explanations too, you know, but it's that I think it's that kids come to science class already having pretty good explanations for some of the, like, their everyday ways of describing and explaining these particular motion phenomena is pretty good. So they already have models for all of this, and it's that I want them to combine their own model with a standard like idea that comes from Newton.
So what would signal a successful achievement on your part as a teacher? Let's say you really wanted kids to understand this explanation as a model, something that's not just that they memorize, but it's a model. What would your kids be able to do then?
I think it's that they would be able to, you know, it might be something like that they would be able to account for if they've practiced with one kind of scenario of maybe everything that they observe when they go bowling or something like that, that then maybe I could say, well, what if it was ice? What if you were bowling on ice? Like a slightly novel case of some phenomena that they've had experience with. If they could then run their explanation in different contexts, or like maybe it would be, you know, objects falling with a parachute. Well, what if there was no air? You know, like if I could take away some piece of the phenomena and they could still run their explanation and talk about, well, because there's no air, it's going to alter this, and this of my original idea, but it's not going to alter, you know, the mass of the object that's falling is still the same, so it's not going to alter something, you know, that they could manipulate some of those ideas in their model and run their explanations in novel cases. I think that's my big goal, is for them to be able to think about slightly different
So
events.
that sounds like when you do some assessments, either in the middle or at the end of the unit, you're going to try to see if kids can generalize whatever they've learned to slightly different situations, right?
Yeah, and that's, you know, those what if kinds of questions become powerful as formal assessments, but they also become powerful ways of like probing kids when you're talking to them, because sometimes, especially students who get good at using the right vocabulary at the right time, that if I can pose one of these sort of novel cases to them, sometimes I can shake them out of just trying to impress me with their vocabulary use and get them to communicate either a fully fleshed out idea or like where they have kind of spotty ideas. So
I see
it
kids
helps me
a lot. I mean, it's really important to make sure kids can't hide behind the vocabulary and just get away with, you know, just a glib answer. And
yeah, I mean, even today on the, you know, first and second day of instruction, when a kid will say something like, "Oh, it's friction,"
yeah,
you know, I don't take for granted that they mean what I think they mean by friction. Like I push them to find out, are they just using this word because they've heard it
Yeah,
as a science word, or do they really have, I mean, maybe they have a fully formed idea behind that word, and that's great.
But you want to hear it,
But I want
right?
to, yeah, I need to know, like, do you have an idea behind that word, or are you just using that word because you think it's appropriate in this context?
Yeah.
To give me that as your answer.
It sounds like you want to know more about that idea, not just as a quizzing them, but you want to operate on whatever their current understandings are.
Yeah, and I don't care right now if they call it friction or sticky or bumpy, you know, that I don't, they're using, you know, if they're using another sort of non-physics word to describe the same idea, I want to know, like, in your bumpiness theory, is that the same thing as a theory of friction? Like, what is it that you've got behind your, behind that word?
Well, that leads me to another question I've got here. So it's about specialized language that you think students would have to know. And by specialized language, I mean both like vocabulary, but also kind of the rhetoric. Is there some special kind of science ways of talking about evidence or explanation that you want to make sure you help kids bridge every day in academic language?
Yeah, so there's definitely a body of like physics specific, Newton specific kind of language. So like inertia, you know, just that's definitely on the level of being like a specialized physics language. But then there's also, even when we were, before this, we did like a semester of chemistry, early sort of chemistry ideas. And so there's some words there, or I guess it's more than words, it's like practices and ideas, like the idea of which part of your science paragraph or your science talk is a claim and which part of it is evidence, you know, that, so that kind of floats from chemistry into physics. So I expect that I can continue to use language like that. I can say, oh, so it sounds like that you're claiming this. Well, what evidence do you have that supports your claim? You know, that I can use words like claim and evidence, and that I've had to build that in all along as being, having a specific meaning in science.
So it sounds like the words like claim and evidence aren't just vocabulary words like inertia, but they're also
it's a practice.
Scientific practice.
Yeah, and luckily here I've also, the whole staff works really closely together to get that same practice going across subject areas. So
like, what would work across subject areas?
So like the practice of tying a claim to evidence, and then we also use language of counter evidence. Like that, we do that from science to history to their literature classes. We use that same language, but we talk about like in history it means this practice, whereas in science it means this kind of practice. And so kids don't come in with all of that kind of robust understanding of how things might be different across subject areas, but as a staff we worked hard to keep that language alive and to be really explicit about.
That sounds like a powerful experience for those kids to go from one room to the next, and they hear, they're bound to hear a lot of different vocabulary because that's unavoidable across subjects, but they have this underlying kind of register of talk about claims about knowledge in general.
Right, and it's, the other thing that I've noticed is that it's been important in setting some norms of how kids are going to be pressed during class. Like it's not, when I was teaching in other contexts and I would ask people for evidence or I would probe a little bit more deeply, kids sometimes would shut down because it feels like they're being put on the spot. But here I don't find that to be the case so much because it's absolutely normal across all of our classes for the teacher, or you'll hear it from peer to peer where it's normal to be challenged, that if you make an unwarranted claim, it's normal here to be pressed for, tell me more about the evidence behind that. Or or to present a piece of counter evidence is like that's a completely normal practice here, and it didn't start out, kids don't start out that way. So
Yeah.
we've just made that part of I think it's a way of changing the intellectual environment of school, where it's not searching for a right answer. A question is not a search for a right answer. It's a search for getting you to tell me all of the evidence that you have for whatever it is that you're claiming.
So I want to finish with a couple of questions about relevance, because it's so important for kids to connect what they're doing in school with their everyday lives. So what elements of the ideas in this unit could kids possibly relate to their own lived experiences? I think it's probably an easy one in this unit.
Yeah, it's really this part of, well, I mean, really science is generally I find it easy to do because it is your natural world.
Yeah, but you're not doing atomic structure.
No, that's true.
You're doing
Right.
force, motion.
Right, so this has been, my students are like 11 and 12 years old, and so I tried to pre-think of things that I know that they experience on a daily basis, like all of our kids ride in buses a lot, whether it's metro buses or school buses. So we have lots of ideas about like stopping and starting and sliding across the seat, turning a corner, that they have these common experiences of being a passenger on a bus or and sometimes a passenger in a car. So I have a lot of questions built into the unit about what does the seatbelt feel like when your mom slams on the brakes, or what does it feel like when you're not wearing a seatbelt and the bus driver slams on the brakes? So there's lots of motion phenomena that they've experienced, but then even today and the other day I heard kids bringing up things like roller skating in a roller rink,
right.
That they had lots of good ideas about how the roller skates feel differently on the roller skating rink. Than
I thought
when
they were talking about ice skates the other day.
No, it was roller skating.
Roller
so she was
skating,
talking
okay.
about going around the rink and then going out into the lobby where it's
you
carpet.
get up on the carpet and
You just kind of roll to a stop. But she was saying, that it's good and it's bad because that way you don't just like completely roll out
Right.
into where all the
Right.
people are.
Yeah.
But you have to push harder on your roller skates. If they were older students, I think there would be some things about driving that I could
Right.
tap into, but since they're all 11 and 12, they don't necessarily have ideas about driving. But we also just had all this crazy snow and ice over the winter break, and so I had posed a question to them early on about like a what if it was on ice kind of question.
So all of a
And-
sudden they can relate
yeah,
to that, right?
At first I thought this might be too much of an abstraction, but a lot of kids wrote in their first homework assignment, they wrote a lot about, hey, I saw this happen. This car just went crazy down the hill by my house.
Yeah.
So there's a lot of everyday sort of motion experiences that it's really, and if they can't relate to an experience like that, it's also really easy to create experiences. We can just all roll something across the floor or slide something across the table, create a ramp, in the classroom and roll things. So it's really easy to create common phenomena that we could all look at and refer to.
So that was another question, and you just answered it about sometimes kids don't have shared experiences in the outside world that they can all come into the classroom and talk about as if everybody's been to
Right.
the beach or been to a
Right.
carnival, but so you can, not only is force and motion something that people have a lot of shared experiences around, but you can create or mimic or model experiences in here that
Yeah.
they can share.
Yeah, lots of them.
Are you thinking about some essential question that you want kids to focus on over a few days that will kind of, your instruction will kind of build towards kids answering a big question?
It's more, I think it's probably like 3 big questions. And
Have you got one that comes to mind?
So one that comes to mind is, that I brought up earlier, is this idea of like, why do I, if I want to keep a constant speed while I'm riding my bike, which most of the kids have bikes, so if I want to keep a constant speed riding my bike or on my roller skates, why do I have to keep doing something? Like, why do I have to keep pedaling or keep moving my feet with my roller skates? And then why is it when I stop doing those things that eventually I roll to a stop? So two sort of connected why questions, like why do I have to keep pedaling to keep moving?
Yeah.
And then why do I, if I stop pedaling, why do I eventually stop moving?
Yeah.